Hey guys, tonight we're going to shrink, drastically, down past the realm of molecules, past atoms, and even deeper into a world where logic bends, time blurs, and reality behaves like a whispered riddle. This is quantum physics, not the intimidating kind in chalk-covered equations, but the poetic, uncanny kind. The kind that quietly governs the world beneath your fingertips and may even shape your very thoughts. Picture it. A single speck of dust hovering in a sunbeam. Now imagine zooming in on that dust until you pass through its atoms, into a chasm of empty space. Not darkness, just absence. Where you expected substance, you find a haunting hum of probability. What you thought was solid is mostly not. You probably won't survive this realization in your usual sense of self. But that's the joy of it. Tonight, you're just a soul curled up under a blanket, ready to drift between wonder and dream. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're listening right now, I'd love for you to post your location and local time. It's kind of amazing to know where in the world we're all falling asleep together. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Quantum physics begins not with answers, but with a strange kind of question. What is real? For centuries, scientists believed that reality was a collection of little billiard balls bouncing around, atoms smashing, obeying strict Newtonian laws, like miniature machines. But in the early 20th century, that tidy worldview cracked open. First, they found that light behaved like a wave. Then, they discovered it also behaved like a particle. It wasn't one or the other, it was both. And not just light. Electrons, protons, and all the so-called stuff of the universe dance this double life. This is the quantum realm, a domain where certainty unravels and possibility takes the wheel. The word quantum itself means how much, a tiny amount, a discrete packet of something. A photon is a quantum of light. An electron is a quantum of charge. In this world, nothing flows continuously. Everything comes in bits and jumps. But here's where things get weird. The more you try to pin down a quantum object, the more it slips away. Ask where an electron is, and you'll get a probability cloud, not a location. Ask what it's doing, and your question changes the answer. You might imagine the quantum world as a kind of shimmering fog, where particles are more like suggestions than things, more like maybes than certainties. And yet, this dreamy fog obeys strict mathematical rules. It's not chaos. It's not whimsy. It's just different. The rules are elegant, even beautiful, but they aren't intuitive. In fact, when quantum physics first emerged, even the scientists didn't believe it. Einstein called some of its implications spooky. Niels Bohr, a founding father of the field, famously told him, "Stop telling God what to do." But quantum theory, strange as it is, works. It predicts outcomes with stunning accuracy. Lasers, semiconductors, atomic clocks, and even the chip in your smartphone owe their existence to quantum rules. Still, understanding the quantum world isn't just about technology. It's a shift in perspective. A deep one. Classical physics, what governs falling apples and planetary orbits, assumes the universe is made of objects with definite properties. Quantum physics whispers a different story. One where particles don't have properties until they're observed. One where cause and effect don't always play fair. Imagine you're walking through a foggy forest at night. Every step reveals a little more, but the mist never fully lifts. That's the quantum experience. What's real depends, eerily, on how and when you look. It's as if the universe doesn't commit to a fact until someone asks a question. And even then, the answer might change depending on the way it's asked. Is it unsettling? A little. But it's also liberating. Because if the foundation of reality is uncertainty, then life itself becomes less rigid, more fluid, more alive. The quantum world teaches us that what we thought was solid is mostly space. That particles can be in multiple places at once. That connection can defy distance. That observation shapes truth. And isn't that a little like dreaming? So tonight, as you close your eyes and drift, you're not leaving the world, you're slipping deeper into it. Past the visible, past the tangible, into the unseen machinery that hums behind it all. We'll explore what atoms are really made of. We'll open paradoxical boxes. We'll meet cats who are both alive and dead. We'll touch the edge of time itself. But first, rest here, in this opening thought. Reality is stranger than it seems, softer than we believed, and more delicate than we ever imagined. And beneath it all, there's a quiet rhythm, a quantum pulse, waiting. There's something oddly comforting about realizing that everything solid around you isn't quite what it seems. Let's begin with your pillow. It feels soft, firm, familiar. Now, zoom in. Imagine peeling back the cotton strands, diving into the fibers, shrinking down until you're no longer looking at material, but at molecules. Zoom further still, until the molecules become atoms. Now, we're in the realm of the impossibly small. You expect to find substance, a kind of hard core. But you don't. Instead, you find emptiness. Vast, almost echoing. At the center of every atom lies a tiny nucleus, a proton or two, perhaps a neutron, and swirling around it, electrons in ghostly orbit. But the distances between these particles? Immense. If the nucleus were the size of a marble, the nearest electron might be a football field away. Everything you touch, your skin, your bed, your breath, is mostly nothing. Just empty space shaped by invisible forces. And yet, we don't fall through the floor. We don't dissolve into the air. Why? It's because of the electric force, the silent architect that keeps atoms intact and your feet on solid ground. Electrons repel each other. And when the electrons in your feet approach the electrons in the floor, they push back, gently but firmly. It's this mutual repulsion, not solid contact, that holds you up. You never actually touch anything. What you feel is the pressure of electric fields politely refusing to overlap. Now consider this. Your body is made of around 7 octillion atoms. That's a 7 followed by 27 zeros. Each one is 99.999999% empty space. You are, in a very real way, more absence than substance. This emptiness isn't a flaw in the design. It's part of the wonder. It's what allows atoms to bond, to vibrate, to interact in complex and beautiful ways. Without all that space, life couldn't dance. But don't worry, this doesn't mean you're a ghost. It just means that what makes you you isn't density or bulk. It's structure. It's energy. It's motion. Imagine the atom not as a static solar system, but as a buzzing cloud. The electron isn't a little marble circling the nucleus. It's more like a probability mist, a haze of where it might be. You can't pinpoint its location until you try to measure it. And once you do, it changes. This is the strange nature of quantum behavior. Electrons, protons, even entire atoms behave like both particles and waves. They don't have fixed boundaries or neat positions. They're smears of possibility. And when you observe them, you collapse that possibility into a moment, one location, one outcome. But until that moment, everything is potential. This view of atoms changed how we see not just matter, but ourselves. The ancient Greek philosopher Democritus imagined atoms as tiny, indivisible balls bouncing through the void. Solid, definite. He wasn't far off for his time. But today, we know better. Atoms are not solid balls. They're dynamic, ephemeral, governed by mathematics and mystery. They hum with energy. Electrons can jump between orbits, emitting tiny flashes of light, photons, as they go. These jumps aren't gradual. They're instantaneous. No in-between, no hesitation. And here's where it gets really wild. Even though electrons seem tiny and insignificant, their behavior affects everything from the color of a leaf to the way your nerves fire. Their subtle quantum jumps are the reason we see color, the reason metal shines, the reason stars burn. They may be small, but they are powerful. In fact, when Einstein first explained the photoelectric effect, how light knocks electrons out of metal, it helped birth the entire quantum revolution. So next time you look in a mirror, consider this. The reflection you see is made possible by photons bouncing off the electrons in your skin. You're looking at a ghostly ballet of light and charge, a quantum performance dressed up as everyday experience. And when you speak, the atoms in your vocal cords vibrate, sending waves through the air, vibrations of nothingness, carrying meaning. These waves move other atoms, stir eardrums, trigger thoughts. A domino chain of quantum events, forming language and connection. Even your thoughts themselves, the electric pulses in your brain, are governed by the same strange forces. Sodium and potassium ions dance across neuron membranes, opening and closing tiny gates. Every memory, every dream, every sense of self is built on the behavior of particles that refuse to sit still. Does it feel dizzying? That's okay. Just breathe. The cosmos is made of these dances. The moon, the oceans, your coffee cup, they all obey the same strange music. What feels solid is just the surface of a deeper, stranger current. So tonight, as you rest your head, remember, you're not resting on your bed. You're hovering, slightly, above it, held aloft by a sea of repulsion between electric fields. A kind of levitation, too small to see but too constant to deny. Reality doesn't sit still. It vibrates. It pulses. It whispers in quanta. And in that whisper, you exist. Let's linger now at the edge of light, not the glow from your lamp or the shimmer of the moon, but the essence of light itself. Because light, too, lives a double life. Sometimes a wave. Sometimes a particle. Always a paradox. We're taught, early on, that light travels in waves, like ripples across a pond. This explains so much: rainbows, reflections, how your sunglasses block glare. But then quantum physics stepped in and said, wait, that's not the whole story. Light also arrives in little packets, called photons. Not endless ripples, but tiny bursts. A photon is the smallest possible amount of light. No halves, no fractions. Just one discrete, indivisible blip. This realization changed everything. In 1801, a physicist named Thomas Young performed an experiment that still echoes through science classrooms and late-night thoughts. The double-slit experiment. Here's how it goes. Take a screen and fire light at it through two narrow slits. If light were made of particles, like paintballs, you'd expect to see two bars on the wall behind, where the light passed through each slit. But that's not what happens. Instead, you see interference patterns, a series of bright and dark bands, like ripples overlapping in a pond. This is a hallmark of wave behavior. The crests and troughs of the light waves either boost each other or cancel out. Wave logic. But here's the twist. Now fire one photon at a time through the slits. Just one. Wait a moment. Then another. One by one, they hit the screen. What should be two tidy lines starts to form the same interference pattern, as if each photon somehow passes through both slits at once and interferes with itself. How? It defies sense. It gets stranger. Place detectors at the slits to observe which path the photon takes, left or right, and suddenly, the interference pattern disappears. The photons behave like particles again. Two stripes. No interference. In short, if you watch the photon, it picks a path. If you don't, it chooses both. What does this mean? It suggests that quantum objects, photons, electrons, even entire atoms, don't have definite states until they're measured. They exist in a realm of probability, of superposition, a place where all outcomes float in potential. Only when observed do they collapse into one reality. This isn't just a philosophical puzzle. It's a measurable, repeatable fact. And it applies not just to light, but to matter. Electrons, too, show this duality. Even fullerenes, large molecules of carbon shaped like soccer balls, can be coaxed into behaving like waves. Everything, at a fundamental level, has this dual nature. Think about it. You, listening right now, are made of atoms, built from protons, neutrons, electrons. All of these behave like waves and particles depending on how we look at them. You're not just a body. You're a blurred waveform of being. Your hands are made of uncertainty. Your heartbeat rides on quantum tides. And still, you feel whole. This is the quiet poetry of quantum physics. It doesn't deny reality, it deepens it. You're not less real because you're made of wave particles. You're more wondrous. Let's pause again on the word wave. In quantum physics, a wave isn't just a ripple in space, it's a wave function. A mathematical cloud that tells us where a particle might be found. Not where it is, but where it could be. Before measurement, the particle exists in a spread of possibilities. Once observed, the wave collapses to one. But until that moment, all potential futures lie side by side. It's like standing in front of many doors, all leading to different rooms. Until you open one, every room is possible. The act of opening chooses the reality. This brings us to an unsettling truth. The universe doesn't always behave until someone is watching. Which leads to one of the most whispered questions in physics. What counts as an observer? Is it a machine? A person? A mind? No one knows for certain. And perhaps that's the point. The quantum world may never fully reveal itself, not because it's hiding, but because revelation changes the revealed. This mystery has fascinated scientists, poets, and dreamers alike. Richard Feynman, the brilliant physicist with a knack for bongo drums and chalkboards, once said, "I think I can safely say that nobody understands quantum mechanics." Not a confession of ignorance, but a celebration of humility. Because sometimes, not knowing is the door to wonder. And sometimes, wonder is enough. So as you lie there, let the thought settle gently on your pillow. Light is a particle. Light is a wave. You are matter. You are energy. And beneath both is possibility. The double-slit experiment isn't just a science demo. It's a cosmic whisper that reality has layers, and they shimmer when you look. Let's open the box. Quietly now. Inside, a cat, neither alive nor dead. Or rather, both. Suspended in a delicate, absurd superposition. Not because of cruelty or neglect, but because of one of the most infamous thought experiments in all of physics. Schrödinger's cat. You've likely heard the phrase before, perhaps as a meme or a joke. But behind it lies a deep, unsettling question about the very nature of reality and observation. Erwin Schrödinger, one of quantum physics' early pioneers, didn't invent this scenario to support quantum theory. He created it to criticize it. He was troubled by what the mathematics implied, that particles don't have definite properties until they're observed. That until you look, a system exists in a blur of all its possible states. So he proposed this cat, not a real one, but an imaginary one, safely locked in a box, with a bizarre mechanism. Inside, there's a small bit of radioactive material. If a single atom of it decays, it triggers a detector that releases poison, killing the cat. If it doesn't decay, the cat lives. Radioactive decay, at the quantum level, is governed by probability. You can't say exactly when the atom will decay, only the chance that it might. So, until someone opens the box, the atom is both decayed and not decayed. The mechanism is both triggered and not. The cat, both dead and alive. In quantum terms, the entire system exists in superposition. Multiple outcomes layered on top of each other, unresolved. It sounds ridiculous. And it should. Schrödinger wanted to highlight the absurdity of applying quantum rules, meant for tiny particles, to macroscopic, everyday things like cats. But here's the rub. Experiment after experiment has confirmed the rules. Particles really do exist in superposition until measured. And as our technology advances, we've started to create larger and larger systems that show the same quantum weirdness. Even small organisms, cooled and isolated, have been coaxed into behaving this way. The cat's fate may not be so metaphorical after all. This leads us to the heart of quantum strangeness, the role of the observer. Why does observation collapse as superposition into a single outcome? Why does reality wait for a witness? Is it consciousness that causes collapse? Or is it simply interaction with the environment? What physicists call decoherence. Decoherence suggests that quantum systems lose their spooky multiple states when they interact with something larger. Heat, air, even stray photons. It's like a delicate soap bubble popping the moment it touches a surface. Measurement isn't some magical mental act. It's just contact, entanglement, entropy. Still, no one fully knows why superpositions collapse. Only that they do. Some interpretations say the universe splits, that every possible outcome of a quantum event happens in separate, branching realities. In one world, the cat lives. In another, it dies. This is the many worlds interpretation. And yes, it sounds like science fiction, but it's taken quite seriously by many physicists. Other interpretations say we've misunderstood the nature of measurement itself. That reality doesn't need observers. That the quantum world simply follows its own bizarre rhythm, indifferent to our gaze. And yet, when we look, it changes. There's a quiet eeriness to that. A sense that the universe holds its breath until you glance its way. You might be wondering, why does this matter to me? I'm not a particle physicist. I don't build quantum computers. But consider this. If particles don't have properties until observed, then reality isn't fixed. It's fluid. It adapts. It listens. This doesn't mean your thoughts control the world. But it does mean that the world is more participatory than we ever imagined. We're not separate from nature. We're entangled with it. When you observe, you alter. When you measure, you choose a path. And just maybe, in a very quiet way, you help the universe decide what to be. Back to the cat. The point isn't whether it's truly dead or alive. The point is that quantum rules challenge our most basic assumptions, that things are either or, that outcomes are definite, that truth is singular. Quantum physics asks us to hold uncertainty in our hands, to cradle contradiction, to accept that sometimes the answer is both. And this is not so unlike life. We are full of unmade choices, of identities we carry but haven't worn, of stories we haven't told. We live in superpositions too, between fear and hope, doubt and belief, sleep and waking. So tonight, as you lie still beneath your blanket, imagine the cat, not trapped, but poised, hovering between worlds, a symbol of the mystery we live in. Not every box can be opened. Not every answer fits inside. But the wonder remains. And so does the question. Now let's dive deeper into that most haunting idea in all of quantum theory, superposition. Imagine standing at a fork in the road. To the left, a quiet path through a forest. To the right, a winding trail along a cliff's edge. In our everyday world, you'd choose one. You'd walk it. And the other would fade into what might have been. But in the quantum world, something different happens. Particles don't pick just one path. They exist in both at once. They take both roads simultaneously, until something forces a decision. This is superposition, the ability of a quantum system to be in multiple states at the same time. An electron can spin clockwise and counterclockwise at once. A photon can go left and right. A particle can exist here and there. It's not indecision. It's a kind of wholeness, a refusal to collapse into simplicity too soon. Let's return to the double-slit experiment for a moment. A single photon doesn't travel through just one slit. It goes through both. It interferes with itself. It doesn't choose a path until we make it choose. Now imagine that on a larger scale, not just a photon, but an entire atom, even a small molecule. Scientists have placed these larger systems into superposition in laboratories, suspending them in overlapping states that defy classical logic. To us, superposition feels unnatural. We live in a world of clear outcomes, yes or no, on or off, alive or dead. But quantum systems live in the realm of maybe. In fact, the mathematics that govern superposition is deeply precise. It's described by the wave function, a complex equation that predicts all possible states and their probabilities. The wave function isn't a guess. It's a tool for foreseeing how the quantum world unfolds. But here's the mystery. The wave function collapses the moment a measurement is made. All the probabilities disappear, leaving behind only one result. One reality. It's as though nature holds her breath, considering all options, and then, in an instant, settles on just one. The rest vanish, not even as memories, but as never was. Why does the collapse happen? No one really knows. Some physicists believe that collapse is fundamental, a natural shift from possibility to actuality. Others think it's not collapse at all, but merely a change in our knowledge. Still others, those in the many worlds camp, believe that all outcomes happen, just in separate universes. In their view, the universe doesn't choose, it branches. But whatever interpretation you prefer, the observable truth remains. Quantum systems live in layered, unresolved states, until they don't. Let's picture this with something closer to home. Say you're drifting to sleep. In one possible future, you dream of floating in space. In another, you walk through your childhood home. In yet another, you simply rest in darkness. Superposition is not unlike this. All dreams lie waiting. The moment your mind drifts into one, the others dissolve. Superposition is not just a scientific idea, it's an invitation. A reminder that the world is more complex than binaries. That potential can exist in quiet tension. That uncertainty can be a kind of grace. It also plays a key role in emerging technologies. Quantum computers, for instance, use superposition to store and process information. Classical bits are either 0 or 1, but qubits, quantum bits, can be both at once. This allows them to solve certain problems unimaginably faster than any classical computer ever could. But to work, these systems must be protected from the outside world. Because the moment they interact with their environment, poof, the superposition collapses. The delicate state is lost. Maintaining superposition is like holding a soap bubble mid-air, hoping no wind, no warmth, no vibration will disturb it. It's fragile. It's beautiful. It's hard. Still, we manage to coax these quantum systems into cooperating, at least for a moment. And in that moment, the future unfolds. So what does all this mean for us? It means that certainty is not the default. That the universe prefers to hover in liminal spaces. That what is only becomes so after brushing against what might be. Maybe we, too, live in states of superposition more often than we think. When we hesitate before speaking. When we weigh a decision. When we wonder who we're becoming. And that's not weakness. It's a feature of being alive in a quantum world. So as you lie there, not fully awake, not quite asleep, consider this. You are in superposition. And that's perfectly okay. Let the possibilities hum around you. Let the wave function hold you. Collapse will come. But not yet. If superposition feels like a gentle riddle, then what comes next feels like a deliberate provocation. Because in the quantum world, it's not just that things exist in multiple states. It's that you, the observer, seem to change what exists. This is the heart of quantum strangeness. The observer affects the observed. Let's go back, again, to the double-slit experiment. When you don't observe which slit the particle goes through, you get an interference pattern. The photon, or electron, or atom behaves like a wave. It explores both paths. But the moment you set up a detector to measure which slit it passes through, the interference vanishes. The particle behaves like a particle, as though it suddenly makes up its mind. That's not just odd, it's revolutionary. The experiment doesn't just test the particle. It tests the nature of reality itself. And it suggests that reality is not independent of our interaction with it. That observation isn't passive, it's participatory. Of course, physicists aren't saying that you, personally, with your human thoughts and emotions, change the universe by thinking about it. The term observer in quantum mechanics refers to any interaction that causes a collapse in the wave function, any point where the system stops being isolated and begins to interact with the environment. But the language matters. Observer. Measurement. It implies that knowledge, awareness, even curiosity, has a role. This bothered Einstein deeply. He believed in a reality that existed independently of whether anyone was looking. "I like to think the moon is there," he once said, "even when I'm not looking at it." But quantum mechanics whispered something else. It suggested that the act of observation, of looking, wasn't just revealing reality. It was creating it. It's a radical idea, and to this day, physicists argue over what it really means. Some believe the problem lies in how we interpret the math. Others believe we need a new framework entirely, one that doesn't require this uncomfortable entanglement between subject and object. Still, the experiments are clear. What happens depends on how you choose to look. There's an eerie beauty in this. Imagine reality as a great, unfinished painting. The canvas is blank, except for the spots where you've brushed your gaze. Every glance, every question, adds detail. The parts you haven't looked at, they remain ambiguous. Not empty, just unresolved. Your attention carves shape from the formless. This isn't magic. It's quantum measurement. But to the dreaming mind, it feels poetic. It suggests that attention matters. Even in quantum computing, this plays a role. Quantum algorithms work by manipulating qubits while they remain in superposition, before measurement. The key is to interfere with the wave function just enough to amplify the correct answers, and only then, collapse the state with a final measurement. Too soon, and the computation fails. Too late, and it decoheres. The timing must be perfect. The act of observation, once again, decides the outcome. Let's bring this back to a gentler thought. Imagine you're sitting in a quiet room. Outside your window, wind brushes the trees. Somewhere, in another country, rain is falling. In another time zone, someone else is hearing this very sentence. All those things exist, but your mind makes none of them real until it turns to them. You are not a passive receiver. You are an agent of unfolding. And this doesn't make you powerful. It makes you part of it. Part of the system. Entangled. We often think of science as cold, detached, pure logic. But quantum physics reminds us that even in the most precise calculations, there's room for mystery, for influence, for entanglement between knower and known. Some interpretations, like the Copenhagen interpretation, fully embrace this. Particles don't have definite properties until measured. Others, like Bohmian mechanics, say particles always have defined positions, and it's our ignorance that hides them. Still others, like relational quantum mechanics, argue that properties don't exist in any absolute sense, only relative to the observer. In other words, what is true may depend on who is asking. That's a staggering thought, and a strangely intimate one. It means that reality, at least at the quantum level, is not a fixed script. It's a conversation, a call and response between what is and what is asked. So tonight, as your mind drifts towards sleep, consider this. You are not watching the universe. You are participating in it. You are not separate from the story. You are a co-author. And as your thoughts slow, as your breath softens, remember, even silence can collapse a wave. Even stillness can stir a truth into being. Now we step into the strangest, most poetic territory of all, entanglement. Imagine this. Two particles are born together in a single event, perhaps from the same spark of energy, the same decay, the same collision. From that moment on, no matter how far they drift apart, across the lab, across continents, across galaxies, they remain connected. Not metaphorically, literally. Measure one, and you instantly know something about the other. Not in a delayed, light speed kind of way. Instantly. faster than any signal could travel. It's as if the two particles share a private language, one that defies space and time. This is entanglement. Einstein called it spooky action at a distance. And it is. Imagine twins born at opposite ends of the universe. One turns left, the other, instantly, turns right. Flip a coin on Earth, and its entangled partner on the moon comes up the opposite. Without any message sent, without delay, without even knowing how. It violates our most basic intuitions about causality, about space, about isolation. But it's real. Experiments have confirmed entanglement countless times. With photons, with electrons, even with small molecules. We've separated entangled particles by kilometers and still found that their states correlate perfectly. This doesn't mean we can use entanglement to send messages faster than light. The correlations are real, but they don't allow controlled communication. Still, the fact that these connections exist, that they persist, is breathtaking. It means that separation is an illusion. That once particles become entangled, they are part of a whole, no matter how far apart they seem. This leads to unsettling implications. If entanglement can stretch across space, could it also stretch across time? Could a particle today be entangled with something not yet born? Could memory itself be a quantum echo? Some scientists explore this with experiments in delayed choice. Others look at entangled photons in time-separated pairs. The math permits it. The universe, perhaps, already practices it. And if quantum mechanics allows these connections, what else might be entangled? Are we? After all, you and I, right now, are sharing a moment. You're hearing words I once formed, perhaps hours ago, perhaps continents away. Our bodies are made of particles that once lived in stars. The breath you take carries atoms once inhaled by trees, by oceans, by other people. The boundary between you and everything else begins to blur. And quantum physics leans in to whisper, that blur is real. Entanglement is at the core of new quantum technologies, too. Quantum teleportation, for example, isn't science fiction. It's a real process. By using entangled particles, information about a quantum state can be transferred from one place to another, without moving the particle itself. It's not teleportation in the Star Trek sense. No atoms are whisked through space. But the state, the identity of the particle, moves. Disappears in one place, reappears in another. Like a secret passed hand to hand by invisible messengers. Quantum networks built on entanglement could one day power unbreakable encryption, quantum internet, even computers that solve in seconds what would take classical machines millennia. But behind the technology is something far more intimate. The idea that everything may be linked. That the universe is not a collection of isolated parts, but a single, vibrating web. A network of relationships. Of echoing states. We often think of ourselves as separate. Your mind behind your eyes, your thoughts inside your skull. But quantum entanglement hints at something older, deeper. That connection is the fabric of being. Maybe the love you feel when you hold someone's hand, the stillness when your pet curls up beside you, the ache when someone far away thinks of you. Maybe these aren't just feelings. Maybe they're echoes of something fundamental. Quantum mechanics doesn't prove this. But it opens the door. And once the door is open, it's hard to close. Tonight, as you lie still, know this. Every atom in your body once touched a star. Every breath you take stirs particles that pass through other lives. And somewhere, perhaps, something you once knew still echoes through entangled light. You are not alone. You never were. Let's now turn our attention to something that lives at the very heart of quantum mystery. Uncertainty. But don't let the word scare you. Uncertainty, in quantum mechanics, isn't chaos. It's not ignorance. It's not a gap in our tools or a flaw in our measurements. It's a law of nature. At the smallest scales, the universe places a firm, graceful limit on what we can know. This is the Heisenberg uncertainty principle, and it says that there are pairs of physical properties you can't know precisely at the same time. The most famous pair: position and momentum. If you know exactly where a particle is, you cannot know exactly how fast it's moving or in what direction. And if you know exactly how fast it's moving, you lose track of where it is. The tighter your grip on one, the more the other slips through your fingers. It's not because your equipment is clumsy. It's because the very act of trying to observe one of those values disturbs the system. You might imagine this like trying to weigh a soap bubble with your hand. The moment you touch it, it changes. It collapses. You cannot weigh the untouched bubble, and that's the point. The deeper truth is even more beautiful. Particles simply don't have exact position and momentum at the same time. Those properties don't exist until measured. Reality, at the quantum level, is not fully formed, it's in flux. Heisenberg's principle applies to other pairs, too. Energy and time, for instance. The more precisely you know the energy of a particle, the less precisely you can know when it had that energy. This uncertainty gives rise to some of quantum physics' most curious phenomena, such as quantum fluctuations, where particles can briefly borrow energy from the vacuum of space, flickering into existence for an instant before vanishing again. Yes, you heard that right. Even nothingness isn't nothing. The vacuum, what we think of as empty space, is teeming with brief, phantom particles that appear, interact, and disappear before they can be measured. Why are they allowed to do this? Because of uncertainty. Because the universe bends its rules just enough, for just long enough, to allow tiny flashes of possibility. This ephemeral dance isn't just theoretical. It's responsible for real, measurable effects, like the Casimir effect, where two metal plates placed very close together experience a mysterious force, caused by quantum fluctuations in the space between them. Uncertainty, then, doesn't mean unreliability. It means richness, a kind of softness woven into the fabric of being, a gentle refusal to snap shut into absolutes. And in many ways, uncertainty keeps the universe alive. Without it, atoms wouldn't form. Electrons would spiral into nuclei. Stars wouldn't shine. In fact, fusion in stars, the process that creates heavier elements, the stuff you're made of, relies on particles tunneling through energy barriers they shouldn't be able to cross. A phenomenon made possible by uncertainty. So the very atoms in your body, the calcium in your bones, the iron in your blood, exist because uncertainty allows the impossible to occasionally happen. It's strange, isn't it? We spend so much of our lives seeking certainty, making plans, drawing boundaries, holding tight to solid ground. But the universe, in its deepest layers, doesn't work that way. It breathes improbabilities. It dances between maybes. This isn't to say that everything is arbitrary. Quantum mechanics is one of the most precise theories in all of science. Its predictions have been confirmed to astonishing degrees of accuracy. But precision doesn't mean certainty. It means understanding the rules of uncertainty, the way possibility distributes itself across time and space. So what does that mean for you, resting here, sinking into the quiet? It means that softness is written into the world. That not knowing can be a kind of truth. That ambiguity is not failure, it's design. It also means that your future, like an electron's path, isn't fully determined. It shimmers. It offers. It waits. Tonight, let go of the need to grasp every answer. Let go of the urge to collapse every wave. Let uncertainty hold you, not as a question to solve, but as a lullaby. You don't have to know what comes next. Neither does the universe. And yet, the stars still shine. The atoms still hum. And your breath still rises, slow and soft, in the dark. Let's follow a particle as it does the impossible. There it sits, calm and contained, on one side of an energy barrier, a hill too high to climb. In classical physics, the rules are clear. If the particle doesn't have enough energy to reach the top, it stays put. Like a ball trapped in a valley, unable to roll over the rim. But in the quantum world, The rules get soft. The particle doesn't climb the hill. It simply appears on the other side. This is quantum tunneling, the delicate, improbable process by which particles pass through barriers they shouldn't be able to cross. Not by force, not by breaking rules, but by following a deeper, stranger logic. It's as if the particle says, I don't need to go over. I'll go through. You might picture it like a ghost slipping through a wall, not damaging it, not opening a door, just reappearing beyond the boundary, untouched. How is this possible? It comes back to the wave-like nature of particles. In quantum mechanics, every particle is also a wave. And waves don't just stop at walls. They bleed into them. They spread. So when a quantum wave reaches a barrier, a tiny part of it seeps through. If the barrier is thin enough, or the particle small enough, there's a real, measurable chance the particle will be found on the other side. It's not magic. It's math. And it's been confirmed in countless experiments. Tunneling is more than a curiosity. It plays a central role in how the universe works. Without it, the sun wouldn't shine. That's right, nuclear fusion, the process that powers stars, depends on tunneling. Inside the sun, protons need to collide with incredible force to overcome their mutual repulsion. But sometimes, they tunnel. They pass through their energy barrier and fuse, releasing light, warmth, and life. Your morning sunlight is built on particles doing the impossible. And it's not just stars. Quantum tunneling is behind the scanning tunneling microscope, which lets us image surfaces atom by atom. It's used in flash memory and plays a role in radioactive decay. Even in the neurons of your brain, tunneling may affect how signals travel between synapses. You are, quite literally, a creature shaped by tunneling. Now imagine this process at a more poetic scale. Barriers in life can feel absolute. Mountains of fear. Walls of doubt. The mind says, I can't. The world says, you shouldn't. But what if, like particles, we are meant to slip through, not by force, but by probability? What if every barrier contains a whisper of permeability, a sliver of grace? Quantum tunneling reminds us that the world isn't as closed as it seems. That sometimes, outcomes don't arrive by breaking things, but by quietly appearing where no one expected. This is one of the most humbling things about quantum physics. It reveals a universe that is deeply permissive. Not careless, not chaotic, but open, flexible, curious. Tunneling also opens philosophical doors. It suggests that events can occur not by direct causality, but by possibility leaking into the forbidden. That existence sometimes flows, not along the path of least resistance, but along the path least allowed. What does that say about you? Maybe, when you feel stuck, when something seems impassable, it's not that you need more energy. It's that you need to lean into your quantum nature, to realize that part of you is already reaching forward, bleeding into the next state, waiting to be found. You are not just a solid object bouncing against life's walls. You are a wave. And waves extend. So tonight, as you lie still, think of the places in your life that feel closed. The doors that haven't opened. The edges you haven't crossed. Know this. Particles pass through walls every second. Stars shine because of it. Atoms dance because of it. And maybe, so do you. The impossible isn't always impossible. Sometimes, it's just improbable. And that can be enough. Now we drift into the quietest place of all, the quantum vacuum. You might imagine it as emptiness. A hollow space between stars, between atoms. A total absence of matter and motion. But in the quantum world, nothing is never really nothing. Even the vacuum, a space with no particles, no heat, no light, teems with activity. It is alive with virtual particles. These ghostly particles are not like the ones we've met before. They don't last long. They flicker into existence, pair up, often as a particle and its mirror twin, an antiparticle, and then vanish again, almost instantly. They don't break the laws of physics. They obey them in a different rhythm. Thanks to the uncertainty principle, for very short periods of time, the universe allows energy to be borrowed. The shorter the time, the more generous the loan. And in that breath of time, particles are born. They ripple into being. They interact. They disappear. This ephemeral dance happens everywhere, even in the darkest, coldest, emptiest regions of space. Even in the vacuum you'd think was silent. These virtual particles aren't just abstract phantoms. Their effects can be measured. In the Lamb shift, for example, slight changes in the energy levels of hydrogen atoms can be traced to these fleeting particle pairs. And in the Casimir effect, two uncharged metal plates placed close together in a vacuum attract each other, not because of gravity or magnetism, but because virtual particles behave differently in the narrow gap between them. The vacuum is not still. It's restless. It hums with possibility. Some physicists call this the quantum foam, a sea of bubbling activity at the smallest scales of space and time. At distances so small they can barely be imagined, Planck length scales, the very fabric of space shudders with these ephemeral fluctuations. It might be here, in this restless foam, that the seeds of universes are planted. Some cosmologists believe that the Big Bang itself may have sprung from a quantum fluctuation, a tiny blip in the vacuum that inflated, expanded, and blossomed into space, time, matter, and stars. The universe, then, might be a ripple in nothing, a fluctuation that never vanished. And here you are, curled beneath a blanket, listening to echoes of that first ripple. What's even more astonishing is that these virtual particles help shape the universe even today. They contribute to the energy of empty space, what physicists call the vacuum energy. This vacuum energy might be responsible for the mysterious force known as dark energy, which is causing the universe to expand faster and faster. In other words, the very emptiness of the cosmos may be what pushes galaxies apart. Nothing is not nothing. It is soft potential, a murmur beneath existence. This isn't just theory. It's in our instruments. Particle colliders like the Large Hadron Collider depend on vacuum states. Lasers and semiconductors feel the touch of virtual particles. They are woven into the machinery of our reality. And yet, they remain elusive, always just out of reach, like dreams upon waking. Maybe that's the most poetic part of all. That beneath everything, beneath atoms, beneath space, beneath even time, there is a field of quiet yearning, of possibility forever whispering, I could be. And from that whisper comes everything. So tonight, let that thought settle like dust in the quiet. That the vacuum is not empty. That silence is not stillness. That nothingness itself contains the pulse of being. Your body, your breath, your very thoughts, all of it dances above a sea of flickers. A cosmic stage lit by particles that never stay. You float on a vacuum that is anything but void. You dream inside a hum. Now let's touch time. Not time as you know it, ticking clocks, aging faces, the steady movement from morning to night, but quantum time, where nothing flows quite the way we expect. In our everyday world, time moves forward. Events unfold in sequence, cause, then effect. The past leads to the present, which gives birth to the future. Time feels linear, solid, irreversible. But at the quantum level, this tidy arrow begins to wobble. In quantum equations, those elegant symbols that describe the movement of particles, time appears as something symmetrical. The math doesn't care if you run it forward or backward. Both directions work equally well. This implies that, fundamentally, quantum processes don't have a preferred direction in time. They are reversible. In theory, an interaction could unfold backward just as easily as forward. That's not what we see in our day-to-day experience. But at the deepest levels, time may not be a one-way road. It may be more like a landscape, unchanging, already there, across which we move, or perhaps are moved. Some quantum interpretations suggest that the future might influence the past. Take Wheeler's delayed choice experiment, a fascinating variation on the double-slit setup. In this version, a decision about how to measure a particle is made after the particle has already passed through the slits. And yet, somehow, the particle behaves as if it knew what choice would be made later. As if the present rewrote the past. Or the future whispered to the now. Of course, this doesn't allow us to send messages to the past. But it raises stunning possibilities. That causality is not fixed, and that time itself may be a more fluid, relational thing than we ever imagined. Time, in quantum mechanics, is strange not only in direction, but in duration. According to the energy-time uncertainty principle, there's a trade-off between how precisely we can know a system's energy and how precisely we can know how long it stays in that state. In quantum systems, time isn't a ticking clock. It's a probability field. This is how particles can borrow energy for a very short time. How they can flicker, tunnel, and interact in ways that defy our everyday understanding. It also leads to another phenomenon, quantum time dilation. At incredibly tiny scales, time doesn't move evenly. Some particles experience time more slowly than others, depending on their interactions, their energy, their environment. And in quantum gravity, a still developing field, scientists attempt to reconcile quantum mechanics with general relativity. In Einstein's world, time bends around mass and energy. In the quantum world, time may be emergent, not a fundamental ingredient of reality, but something that appears when systems interact in complex ways. Some researchers even propose that time is an illusion, that what we experience as now is just a perspective, a slice of a much larger, timeless structure, that all moments exist at once, and what we call time is simply the order in which we're able to experience them. It's unsettling, but also freeing, because it means you're not trapped in a one-way current. You're part of a wider tapestry, and your place in it is both fleeting and eternal. You've already lived through countless nows, and you'll live through countless more. The past doesn't vanish. The future doesn't rush to be born. They are all stitched together, shimmering behind the curtain of what your mind can hold. Even dreams, perhaps, are echoes across that timeless space. So tonight, as you breathe deeply, feel time loosen its grip. Forget the hour. Forget tomorrow. Let go of what you should have done. There is only now. And now. And now. Each one as true as the last. Each one quietly eternal. Beneath the particles, beneath the waves, beneath even the emptiness of space, there is something deeper. A silence that sings. A stillness that shivers. A kind of universal canvas from which everything arises. This is the world of quantum fields. It's tempting to think of particles as the fundamental building blocks of reality, as tiny marbles that build up atoms, molecules, matter. But quantum physics offers a more profound idea, that particles are not things in themselves. They are ripples, disturbances, temporary excitations in invisible fields that stretch across all of space. Every type of particle corresponds to a different quantum field. There is an electron field that fills the entire universe, a photon field for light, a quark field for the building blocks of protons and neutrons. Even the famous Higgs field, which gives particles their mass, is everywhere. You are not made of particles. You are made of field ripples. Standing waves in an invisible ocean. To picture this, imagine a vast, calm lake stretching in all directions. A single drop of rain hits the surface, and ripples expand outward. That ripple is a particle. It moves. It interacts. But it is still part of the lake. In this view, the universe isn't built from objects, but from vibrations. From energy that flickers into patterns. Reality is less like a machine and more like a song. The standard model of particle physics, our best attempt to describe the fundamental forces, rests on this idea. All matter and forces emerge from fields. Particles are just quanta, discrete packets, of these underlying fields. A photon is a quantum of the electromagnetic field. An electron is a quantum of the electron field. Even you, listening now, are a layered chorus of these excitations. And these fields aren't optional. They don't float within space. They define space. Even in the vacuum, the fields remain. Even in absolute zero, they tremble with energy. This trembling is what allows particles to appear from nothing, what enables tunneling, what fuels the Casimir effect and the Lamb shift. Space isn't empty. It is pregnant with structure. This changes how we see identity itself. A particle isn't a standalone thing. It's a momentary expression. A note in a symphony. A pulse in a fabric that never ends. Even the idea of a point particle is misleading. What we call small is just localized, a tightly focused ripple in a much larger, all-encompassing wave. And sometimes, when those ripples grow unstable or interfere in just the right way, new particles can be born, or vanish, or change. This is how high-energy collisions in particle accelerators create new matter. We're not smashing particles like billiard balls. We're shaking the fields hard enough to make new ripples. And those ripples, fleeting though they may be, are real. They can be tracked, measured, even weighed. The elegance of quantum field theory lies in its unification. It says that the universe isn't made of separate parts, but of one field per type, layered and interwoven, dancing according to deep, invisible symmetries. Even gravity, though not yet fully understood in quantum terms, may eventually reveal itself as another ripple. Another layer of the universal song. Some researchers pursue this dream through theories like string theory, where particles are seen as tiny vibrating strings, and their pitch, their vibration, determines what kind of particle they are. Whether string theory is true or not, the core idea remains. What we call matter is music. What we call space is stage. And you are both the listener and the melody. So as you rest in the stillness of night, remember, the quiet is not empty. It's filled with fields you cannot see, fields that once rippled to form the breath in your lungs, the atoms in your pillow, the starlight on your skin. The deeper you go, the less you find, and the more you realize. You are made of everything, and everything is made of waves. Now let's step back, just a little, and take in the bigger picture. Because as wondrous as quantum mechanics is, it's only part of the cosmic story. There is another theory, equally powerful, equally beautiful, that governs the very large, stars, galaxies, gravity, and the fabric of space-time itself. That theory is Einstein's general relativity. And here's where things get complicated. Because quantum mechanics and general relativity don't agree. One rules the small with precision and probability. The other rules the large with geometry and grace. And yet, when you try to bring them together, when you ask how gravity behaves at the quantum level, they clash. Relativity sees space-time as a smooth, continuous fabric. Massive objects bend this fabric, creating gravity. Planets orbit stars not because they're being pulled, but because they're following curves in space-time. Quantum physics, on the other hand, says that nothing is truly smooth. Everything fluctuates. Even empty space. Even time. Especially at small scales. When you try to apply quantum rules to gravity, when you zoom into the bends and curves of space-time, you find chaos. Infinities. Equations that break down. This conflict is more than a mathematical inconvenience. It's a deep philosophical tension. One theory is deterministic, the other, probabilistic. One flows like a river, the other jitters like a flame. Both are spectacularly accurate in their own domains. But in places where the very small and the very massive collide, like inside black holes, or at the moment of the Big Bang, our two great theories can't speak the same language. This is the central challenge of modern physics, to find a unified theory. A single framework that merges gravity with quantum mechanics. A way to describe everything from the quarks inside a proton to the curvature of space-time around a galaxy. Some believe the answer lies in string theory, where particles are replaced by tiny vibrating strings. Others explore loop quantum gravity, which tries to quantize space-time itself, breaking it into discrete chunks, like atoms of geometry. Both approaches are promising. Both are incomplete. There are other contenders too: causal dynamical triangulations, asymptotic safety, emergent gravity. Each offers glimpses of a deeper reality, yet none has delivered the final, harmonious equation. Still, even in this discord, there's beauty. It reminds us that science is a living thing, a process, a journey. Our theories are not static truths, but evolving maps, refined with each discovery, each experiment, each dream. Sometimes, we imagine science as a towering edifice, but it's more like a coastline, always changing, shaped by tides of thought and waves of evidence. Some cliffs stand for centuries, others crumble overnight. And the space between quantum mechanics and relativity, that's where the fog lies thickest, where the mystery is greatest, where the next revolution may begin. Perhaps the tension between the two is not a flaw, but a feature, a clue, a signpost pointing beyond both, toward something richer. Maybe the universe isn't meant to fit in one box. Maybe it speaks multiple dialects. Maybe it sings in harmonies we haven't yet learned to hear. And maybe that's okay. After all, you, too, are made of contradictions. You are logic and emotion, dream and memory, quantum and cosmos. So tonight, let go of the need for everything to align. Let the tension be a kind of music. Let uncertainty and curvature sit side by side, like waves brushing against shorelines. The universe is not a solved puzzle. It is a poem still being written. And we are all somewhere between the lines. Now, let's return to the world you live in, your home, your hands, your heartbeat, and discover just how deeply quantum physics already shapes your life. Because while most of this journey has been invisible, intangible, and strange, quantum theory isn't just a theory. It works. It powers the world around you in ways so ordinary, they almost go unnoticed. Let's start small, your phone. Inside it, billions of tiny transistors turn on and off, creating the digital symphony of your messages, your photos, your streaming playlists. These transistors depend on quantum tunneling and semiconductor physics, both of which were once bizarre theories. Your entire digital world, your browser history, your navigation apps, your playlists of sleepy science videos, exists because electrons behave like waves. Now imagine getting an MRI scan. The incredible clarity with which doctors can see your brain, your muscles, even the water in your cells, that's quantum physics at work. Magnetic resonance imaging depends on the quantum property of spin, a kind of intrinsic angular momentum carried by particles like protons. Without understanding quantum spin, medicine would still be looking through X-ray eyes. The deeper, gentler view wouldn't exist. Even your alarm clock owes a debt to the quantum world. The most accurate clocks on Earth are atomic clocks, which measure time by tracking the vibrations of electrons jumping between energy levels in cesium atoms. These clocks don't just keep your morning routine in sync. They anchor GPS satellites, ensuring you know exactly where you are, even if you're just looking for the nearest coffee shop. Without quantum timing, your GPS would drift, your location would blur, and the system's guiding planes and ships would lose their way. Let's zoom out even further. The field of quantum cryptography is already here, offering encryption so secure that even the most powerful supercomputer would take eons to crack it. Why? Because any attempt to observe the encryption key changes it, thanks to the measurement problem you've already met. Then there's quantum computing. Though still in its early stages, it's one of the most exciting frontiers in technology. Instead of classical bits, zeros and ones, quantum computers use qubits, which can exist in superposition, both 0 and 1 at once. When entangled, these qubits work together in ways no classical system can replicate. They're not faster in the traditional sense, but for certain problems, like simulating molecules, optimizing complex systems, or breaking certain kinds of encryption, they can perform tasks in seconds that would take traditional computers millions of years. In the future, Quantum computing could revolutionize chemistry, pharmaceuticals, logistics, climate modeling, and even artificial intelligence. But even today, humble, ordinary quantum technologies touch you all the time. Laser pointers, barcode scanners, LED lights, solar panels, all born from discoveries in quantum theory. It's astonishing, really, how something so ethereal, so counterintuitive, has become the scaffolding of modern life. And yet, that's often how progress works. What begins as mystery becomes machinery. What once felt like magic becomes mundane. But don't let familiarity dull the wonder. Because every time your phone pings, every time a satellite guides your path, every time a lab sees inside a human body without cutting it open, that's quantum physics speaking softly behind the scenes. It reminds us that the most powerful forces often act invisibly. That behind every click, every glow, every signal, there is a ripple. So tonight, let your pillow cradle you the way the Higgs field cradles mass. Let the lead by your bedside hum with a soft quantum whisper. And as you drift off, remember, you are already living in a quantum world. Not tomorrow. Not in the lab. Now. We've journeyed far, from ghost particles and shimmering wave functions to the strange clocks of atoms and the trembling stillness of the vacuum. But before we rest completely, let's ask one final question. One that bridges the scientific and the spiritual. Are we quantum beings? It's tempting to separate ourselves from the theories we've explored, to treat quantum mechanics as a curiosity of the very small, something that happens beneath microscopes or in the void between galaxies. But is it possible that quantum physics doesn't just explain the universe, but permeates us? After all, we are made of atoms. Each atom is built from particles that exist in superpositions. Each electron in your body tunnels, entangles, spins. In that sense, we are undeniably quantum. But there's more. Some scientists and philosophers have long wondered whether consciousness itself might arise from quantum processes. That the brain, the most complex known object in the universe, isn't merely a biological machine, but a quantum system. This idea is controversial. Some dismiss it outright. Others find it intriguing. One such theory, called orchestrated objective reduction, OR, suggests that consciousness arises from quantum activity inside microtubules, tiny structures within neurons. That our sense of self, our awareness, might stem not from ordinary chemistry, but from delicate quantum coherence. If that's true, if even a sliver of it holds, then we are more than machines. We are quantum listeners, quantum choosers, entangled not just with the universe, but with possibility itself. Even if consciousness isn't quantum in nature, the metaphor remains beautiful. Because life, too, is full of superpositions. Moments where we live between choices. Emotions that blend. Thoughts that shimmer in multiple directions before collapsing into words or actions. To live is to collapse wave functions, again and again. To walk the fine line between dreaming and waking. To be unfinished, constantly resolving, constantly beginning. Even memory behaves like a quantum system. Every time we recall something, we change it. Each observation collapses it into a slightly new form. Your past, like a particle, is not a fixed archive, but a set of potential stories, shaped by the act of remembering. And so maybe the question isn't, are we quantum? Maybe the question is, how could we be anything else? We exist because of tunneling in stars. We see because photons bounce off our retinas. We touch because of fields and repulsion and probability. We speak and think and remember through patterns laid down by waves, not certainties. Even love, perhaps, has quantum echoes. The way two people can be apart but still affect each other. The way presence sometimes exceeds proximity. The way understanding collapses distances. So tonight, as your eyes grow heavier, rest in this. You are not made of things. You are made of relationships, of fluctuations, of potential resolved through attention. You are not a solid object. You are a ripple in fields older than time. And just like every particle you've met on this journey, you shimmer in possibility until you choose to become. And now, we let it all go. The waves, the particles, the cat in the box, the clocks in the atoms, the fields that stretch through space like invisible silk. Let them soften. Let them dissolve. You don't need to remember the terms, the theories, or the thought experiments. You don't even need to hold the mystery. Just let it drift. Let it sink into the dark like starlight into water. Let it echo quietly inside your chest, not as fact, but as rhythm. Your breath is quantum. Your stillness is alive. You, curled gently under blanket, are part of this grand unfolding. Everything you are, your thoughts, your skin, your sleep, is part of the same soft equation. And tonight, that equation hums in perfect balance. The fields stretch on. The stars whisper improbability. And somewhere, deep beneath your pillow, a particle waits to be found. You don't need to look. You just need to rest. So close your eyes now. Let the universe be strange. Let it cradle you in superposition. Let it carry you, without judgment, across the blurry edges of dream and reality. Time doesn't matter here. Outcomes don't matter. You are the ripple. You are the field. You are the quiet between the questions. And everything is already okay.